Okay, welcome to another Ginger Mathematician video where I'm going to finish off this paper and have a look at the modelling section of this paper 6 from March 2021. And if you're liking the content, then do hit that like button and think about subscribing as well. It goes a long way to supporting the channel. Right, let's get started. So we're looking at an enclosure for cats, and you're advised to spend no more than 50 minutes on this part. And we're given some very useful formulae for the volume of a cylinder, cone and sphere, and we're looking at modelling the floor area and volume of enclosures for cats. And Dorothy has got 2 cats and she wants to build an enclosure for them. How nice. And we're going to look at three designs as we go through the question. So design 1 is a cone like so, and design 2 is a hemisphere, so half a sphere, and the cone and the hemisphere have the same diameter d. And the first thing we need to do is show that the volume of the cone is equal to this expression here. So the first thing I'm going to notice, if I go back, so this is a non-linear paper, you need to go back and forward, is that we have the formula for the volume of a cone, but notice the formula contains the radius and not the diameter. So to show the examiner, I'm going to copy across that formula. So V equals 1/3 pi r squared h, and what we want to do is use the information in the question to then hopefully, fingers crossed, make this formula. Well, let's have a look at the radius. So remember, the radius is from the center of the circle to the circumference to the edge, and if the whole thing across is d, then the radius is going to be half of that, so it's going to be half of d, which we generally like to write as d over 2. So notice these two things are exactly the same. So all I'm going to do here is wherever I see an r, so the radius, I'm going to replace it with a d over 2. So let me get that trusty highlighter out. So wherever I see an r, there we are. Now I'm going to replace it with d over 2. So let's go and do that now. So we've got 1/3 pi. Now the r is going to be replaced by d over 2. Then we're going to have that all squared and then multiplied by the height. Right, let's see if we can get further through this. So we've got 1/3 pi. Now if we're squaring, it's timesing by itself. So essentially what we're doing here is d over 2 times d over 2. So to multiply fractions, we times the tops and times the bottoms. So d times d is d squared, and 2 times 2 is 4. So I'm going to replace this now with d squared over 4 times h, and we're kind of getting there now. So we're just going to sort this out. So let's sort out the numerator first of all. So you've got 1 times pi, let's leave pi at the top, numerator d squared, and the numerator h. Notice all those could be written as pi over 1 or h over 1. And if we do the bottom part here, well, 3 times 4 is equal to 12. And we get exactly the expression that we're looking for there. And again, on these modern papers, they actually tell you how many marks there are per question. Now in part 2, they want you to do a very similar thing, but this time for the volume of the hemisphere. We need to write it in its simplest form in terms of pi and d. So no h's, just pi and d. So if we go back, we're going to do the same analysis that we did before. Now the volume of a sphere is, radius r, is v equals 4/3 pi r cubed. So let's write that in so the examiner knows what we're working with. However, we do not want a full sphere, this 4/3 pi r cubed. We want a hemisphere, so half of that. So if we want to get half of that, the volume of a hemisphere, so I'll put hemisphere, it's going to be half of that. So instead of 4/3 of it, we're going to get 2/3 of it instead. Pi r cubed. Okay, so this is the volume of a full sphere, whereas this is the volume of a hemisphere, just half of the formula that we're given. Again, we can do a similar process to before. So notice if this is d, then this is going to be d over 2 in the same way I explained here. So a similar process, wherever I see an r, I'm going to replace it with a d over 2. So we get 2/3 pi, and we get d over 2 all cubed, and we're going to work this through a similar way. So remember, d over 2 all cubed That's the same as doing d over 2 times d over 2 times d over 2. Well, that gives us d times d times d is d cubed at the top, and 2 times 2 times 2 is equal to 8. Again, just taking it one step at a time, guaranteeing I'm getting those communication marks, which are really important. So I get d cubed over 8, like so. And now we can simplify this a little bit further. So we have 2 times pi times d at the top, or d cubed, and we get 24 at the bottom. Now notice this is where I highlighted this part of the question. We are not finished at this point because we can simplify this further. So 2 goes into 2 once, 2 goes into 24 12 times. So the final answer, making sure we get all 2 marks here, is pi d cubed over 12. And we're done. And on to the next question, again 1 mark, so it can't be too much work that we're expected to do here. Write h in terms of d. Okay, so when h equals something d, when the volume of the cone is equal to the volume of the hemisphere. So we're going to take the 2 answers we've just worked out here. So we've got the first answer, which was pi d squared h over 12. That's the volume of the cone. Notice it's a non-linear paper. You're using answers from before to help you what's going on next. So pi d squared h over 12, and that's equal to what we just worked out here. So pi d cubed also over 12 as well. Okay, and we can cancel a lot of things here, which is very, very useful. So the 12s cancel, nice. The pi's cancel from both sides. And let's write this out a little bit further. So d squared h is equal to d cubed. And in fact, we can actually simplify this further. We can divide by d squared on both sides. Probably a slightly longer way of doing it. So what we're going to do here is divide by d squared on both sides, just so you can see what's going on here. And this cancels, which is great. So we get h equals, and then d cubed divided by d squared. Remember your index rules. This is d to the power of 1, also known as d. So h is actually going to be equal to d in this situation. And if we look at now part C, part I, find the volume of the cone when h is equal to d over 2. Write your answer in its simplest form, so very similar to one of the previous questions we did. So again, non-linear paper, let's go back. Let's look at the volume of the cone. That's this expression here. So pi d squared h over 12. So v equals pi d squared h over 12. And now we're going to do another substitution. Let's get the old trusty highlighter out. So wherever we see an h, we're going to replace it with d over 2. They're using the information from the question. So we're going to get pi d squared d over 2 over 12. Okay, so let's think how we want to simplify this further. So probably the easiest way to write this is a half pi d cubed over 12. Okay, so I brought the half to the front. D squared times d is d cubed. And if you do a half divided by 12, that's the same as dividing by 24. So then we get pi d cubed over 24. If you're not sure about that step there, have a think what a half, if you divide that by 12, well, that's the same as doing a half times 1 over 12, and that's equal to 1 over 24. So it's really useful to have those fraction skills at the ready so you can simplify in the way that they want you to. So we get our answer here of pi d cubed over 24. And now we need to decide which is smaller. The volume of the cone in part C, part 1. So I'm going to put cone. Really, as soon as I see bold, I'm really following those instructions. So pi d cubed over 24. Or the hemisphere, so I'm going to put hemi. And if we go back, the volume of that was pi d cubed over 12. So pi d cubed over 12. And we want to work out which is smaller. Well, we've got the same numerator in both here. So if we get the highlighter out. we've got the same numerator, so exactly the same. The only difference is with the cone, we're dividing by 24, and with the hemisphere, we're dividing by 12. So here, we're dividing by 24, where here we're dividing by 12. So therefore, this one must be smaller. So notice the very smooth way I've justified that by going, well, they're basically the same thing. One you divide by 24, one you divide by 12. So it's the cone that must be smaller because we're dividing by 24. Okay, and you can look through the answers here. So you can see where we pick up those communication marks. Remember, this C1 here stands for a communication mark to show the examiner exactly how you're working through these problems. Right, on to question 7. And now we've got some extra information about the cat enclosures. So per cat, so for each of the cats, they need a minimum floor sleep area of 0.5 square meters. They need some exercise room of 2.8 square meters. And then finally, an extra floor area for each of 1 square meter. And we need to show the total minimum floor area for 2 cats is 8.6 square meters. Well, for 1 cat, we just need to add together all the necessary areas together. So we add together 0.5 plus 2.8 plus 1. And if we add those together, we get 4.3 square meters. Of course, you can do this on a calculator. And so for 2 cats, we're going to need to double that. So we're going to have to times the 4.3 by 2. And then that gives us then 8.6 square meters, like so. So we've confirmed that they need 8.6 square meters. And now we need to calculate the diameter that gives this minimum floor area. Notice looking for the area here for both the cone and the hemisphere. Well, if we go back, remember this is a non-linear paper, you'll see here that the area of both the enclosures at the bottom are both circles. So what we're going to do here is we're going to work out the radius first of all. Now we're going to use the formula for the area of a circle. So you need to know this, the area of a circle is equal to pi r squared. And we're told that the minimum floor area required is 8.6. So we're going to make this formula equal to 8.6, and then we're going to work out the radius to start with. So we want to get r on its own, so we need to work through our equation skills. What's the opposite of timesing by pi? Well, we're going to divide by pi on both sides. This cancels, leaving us with r squared equals 8.6 over pi. And then when you think what's the opposite of squaring something? Well, that's going to be square rooting on both sides. And then we can work out the radius, which is equal to the square root of 8.6 over pi. So let's go over to my calculator and let's work out what that is. So make sure you have your graphical calculator ready because it's a very, very important tool. I'm in the normal calculating section here, and I'm just going to work out that calculation we needed to work out. So we're going to do 8.6 and then divided by pi. So notice the pi button is down here. And this will give us the radius. So press enter and it will give us the radius. However, if we look at the question, we're actually looking for the diameter. So how do we go from radius to diameter? Well, we times by 2. So I'm going to take my answer and times that by 2. And that gives us the answer for the diameter. So we want to round this to 3 significant figures. So it's going to be 3.31. So I'm going to go back. So we actually want the diameter. So we want 2 lots of this. Put dot, dot, dot. And remember the calculator gave us 3.31. And that's going to be in meters. So one of the key things to watch out about the question, we want the diameter here for the question, not the radius. So that's why we times by 2. And now we need to explain why a hemisphere with this minimum floor area is not a suitable enclosure. Well, let's go back again. Let's look at the hemisphere. Notice that this height here of the enclosure is equal to the radius that we just worked out. So if I go back to my graphical calculator, you'll remember the radius was equal to 1.65. So if I go back to what we're just looking at here, so the radius is equal to 1.65 meters for Hemisphere. Now notice this is not true for the cone, because that was a different variable. It wasn't the r part here. That was equal to h. So notice that was the difference between the cone and the Hemisphere. So this radius here is equal to 1.65 meters, and this is less than this condition I mentioned earlier, that the highest point above the floor must be 2 meters or more. And so this number 1.65 is less than 2, therefore not, I'm going to write this in big letters. Get the pen out, there we are. Not suitable. Make it very clear to the examiner. What I'm saying here, this 1.65 we worked out earlier from here is less than 2. And you can check through the answers and what we've done here in terms of where you get your communication marks. On we go to question 8, and finally Dorothy's made a decision, that's good, to have a volume of 10 cubic meters for the enclosure for the 2 cats. Now this is really important in this kind of paper. Whenever you see something bold, that's telling you go back to that part and use that in some way. So using question 6ai to find a model for h, you want h equals something, ... in terms of pi and d for the cone enclosure. So let's go back, 6ai, that was this formula here. So the volume of a cone is pi d squared h over 12. Okay, so we're going to copy that across. V equals pi d squared h over 12. So I'm just copying over that information, guaranteeing that communication mark as well. And what we need to do is, well, we're saying the volume needs to be equal to 10. So in this case, we're going to do equal to 10. And notice we want a model for h. We want h equals something. So at this stage, what we need to do is make h the subject. A very important skill on the modelling section of paper 6. So let's go through this one step at a time, work out h on its own. So the first thing we do, well, we want the opposite of divide by 12, so we're going to times by 12 on both sides of the equation. This cancels, lovely, so we get pi d squared h is equal to 10 times 12, 120. And then we want to get h on its own, so what's the opposite of timesing by pi d squared? Well, dividing by pi d squared on both sides of the equation. If we do this, this cancels, which is what we want, h, and then we get 120 divided by pi d squared, which is our answer here. So I'm going to write that very clearly for the examiner, so they know that is my final answer. 120 over pi d squared, like so. And now comes a very typical thing they expect you to do on the modelling paper, which is to do a sketch of the model for this particular set of axes, and this is where the GDC comes in. So as soon as you see a graph sketch on your modelling paper, you know there's going to be a graphical calculator element to it. So let's go over. Remember, we're going to work between a scale of 0 to 12 and 0 to 12. Let's pop it in and see what happens. So we are going to go to the on button, and we go to new, and we're going to go for graph this time. Now, in order to make it less confusing when we actually put the function in, we're going to go to menu first, window, and window settings, so we can set it the same way as the axes in the question. So we want to go from 0 to 12, and we also want to go from 0 to 12 here as well. So we'll have it ready to go when we write the function in. Now remember, the calculator doesn't work with the letters that we have, H and D, so we need to work with Y and X. So if I go back briefly, this is the function we're going to type in. So instead of a D, I'm going to type in an X, but leave everything else the same. So we get fraction button, 120, which needs to go, of course, at the top here, 120, over our pi button down here, just a pi button, I don't want any of that, there we are. Okay, and then we've got x down here, and then squared. Okay, so I've typed it in, press enter, and I get the graph that I'm looking for here. So all we need to do is sketch that. Notice it starts over here. It doesn't start right over here, but it starts here. And then making sure we don't touch the axis at the bottom. So we're going to sketch that across. Doing our best sketch that we can. So remember, we have to start over here. It goes down, 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 down. Just make sure you do not touch this axis when you draw your graph. That's really important. Remember, it's only out to 2 marks. You'll see the mark scheme in a moment. And those are the key things to watch out for. The shape of the graph, and make sure this line does not cross this axis here. Okay, and on to part C. So we want to find the total floor area of the enclosure when the height of the cone is equal to 2 meters. And we're actually going to use some working that we've already done before. So notice I'm going to use this highlighted part here. So pi d squared h is equal to 120. So I'm going to copy that across, because now we actually have some extra information we can use then to work out the diameter. So this time we're told now that h is equal to 2. So we can pop that into our equation. So pi times 2 is equal to 2 pi. We can leave the d squared alone for the time being, equals 120. Then at this point we can go, well, I want the d on its own. So what's the opposite of timesing by 2 pi? Well, divide by 2 pi on both sides. That again gives us d squared is equal to 120 over 2 pi. And then what's the opposite of squaring? Well, we want to square root on both sides of the equation. That cancels out the squared, and we get d is equal to the square root of 120 over 2 pi. Remember, the square root goes over everything here, so that's very, very important. And now we can actually work out the total floor area here, so TFA. Remember, that's just going to be equal to the area of the circle at the bottom. So that's going to be equal to pi r squared. So that's our usual formula. So notice here in the formula, we're using the radius, not the diameter. So to go to the radius, we just need to take this and divide it by 2. Now, there's a couple of different ways we can write this. I'm going to write this as a half of 120 over 2 pi. That's going to make it easier when I put it into the formula. So if I put it into here now, we get pi, open brackets, 1/2 the square root of 120 over 2 pi all squared. Notice I've really tried to avoid rushing to my calculator until I've really need it at this very last part. So what we're going to do very carefully, we're going to type this into the calculator and it will do all the hard work for us. So let's pop it in. So we get, first of all, pi. So let's pop that in. Now my pad's working weirdly. So here we go. So open brackets, we're going to write in 1/2. So 1 over 2. And then we're going to multiply that by, and now we want a square root. And we don't want a squared there. And we want a fraction button. So 120 at the top, 2 pi at the bottom. So I'm just copying out very carefully exactly what I've shown before. And then we want to square that at the end. So if you look at this calculation I've just written here, and this calculation written here, make sure they are exactly the same. So we've got this here, we've got this here, and then we press the enter button. And nice, because we haven't got any rounding beforehand, we get a very precise answer here of exactly 50. So we can go back, and we can confidently say now that this is just equal to 15 exactly. Okay, so the area will be 15 square meters. If we had worked some of these out beforehand, we wouldn't have got such a precise answer. We get either 15.01 something or 14.9 something. So it's really important to make sure you get that nice and precise. And there is the mark scheme. I decided to do this approach for part C, but as you can see, there are different approaches you could have taken as well. Okay, and on to question 9. So design 3 now is a half cylinder, just like we see here. And it has diameter D and length W. And use the information on page 10 to write down the smallest value of D. So what they're referring to here, if I go right back, is this part here. So the highest point above the floor must be 2 meters or more. So if we go back to our cylinder, this means that this has to be at least 2. So therefore, because the radius is half the diameter, that we know then that the diameter has to be at least 4. So yeah, the smallest value of D, smallest value must be equal to 4. So remember, when they say use the information here to do this, you really do need to go back and read that carefully. And now we need to show that the volume of this half cylinder is equal to pi d squared W over 8. Now, go right back to the beginning. We actually got given the formula for a cylinder. It is here. So V equals pi r squared h. Now notice we don't have a full cylinder here. We actually have a half cylinder. So the volume of the shape is going to be pi r squared h, but then we divide by 2 because we've got a half cylinder. Now, of course, we're actually using the letter here D instead of R. This is very similar to an earlier part of the question. So remember, R is equal to diameter divided by 2. So we're going to substitute that in. Notice we don't have the height here. We actually have W as our letter. So we put both of those in. We get pi times D over 2 squared times W over 2. Very similar to a calculation we did before. And now we square this. So remember, times D by D, that's D squared. 2 times 2 at the bottom is equal to 4 times W over 2. And now we can bring the divide by 4 downwards. So we then get the formula that we're looking for, which is pi d squared W over 8. One of these where you can use the kind of the show that to actually help you with some of the calculation here as well. So we do get the formula that they wanted. And now we need to show the model for W for a half cylinder enclosure that has a volume of 10 cubic meters is this. We do this in a very similar way to a previous part of the question. So we take pi d squared W over 8. So even if you didn't get B right, we can still use it. And we're going to make that equal to 10. And we go through our usual equation solving here. So what's the opposite of dividing by 8? We times by 8 on both sides. That cancels. We get pi d squared W. You do need to show these steps to make sure you get all the marks. And then we want W on its own. So what's the opposite of timesing by pi d squared? Well, we divide by pi d squared on both sides. This cancels. Lovely. We then get our answer of W equals 80 over pi d squared, which I'm going to write very clearly to the examiner that you know I've got to the right point. And just like in the previous question, they want us to do a sketch of this. Notice here we've got the length, so W and then D. So just like we did before, we're going to go to our GDC and go and sketch it. So we're going to go over to the graph part here. So we're going to have new. We'll go for a whole new document here. And again, just like before, instead of using D, we're going to use X, but everything else stays the same. So we go control 80 divided by pi x squared. I'm going to do this in a different order to what I did last time, just to show you that when you do this without changing the window settings, you'll get kind of a weird graph here. But remember, we want the axes between 12 and 12, just like last time. So you can always do this in either order. So you go to Menu, Window Settings, and we're going to change both between 0 and 12. So just going to change it across. If you're liking the video, by the way, please do think about liking and subscribing. It does help the channel grow. And there we are. We get a very similar graph to what we had before. You can move this around, by the way, to drag it out the way of the graph. So again, similar to how we drew the previous one, making sure we start over here and making sure that we do not go through the axis. A little bit weird there, but it gets you all the 1 mark. Remember, it's very similar to what we did before. And now they tell you the total floor area is 8.6 square meters. And now to work out a model for W in terms of D. This is not as hard as it looks. Remember, non-linear paper. Notice the floor area here is just a rectangle. So the area is just equal to length times width, W times D. So if I transfer that across, well, our W times D, the area, is equal to 8.6. And then we want to get W on its own, what a model for W. So we just divide both sides by D. This is easier than it looks. If we do that, we can cancel and then get W equals 8.6 over D. So this was not as difficult as it looks. Remember, you've got a rectangle this time at the bottom, not a circle. And now it wants you to sketch the model from part DI, so this, onto the previous graph. So let's go back to my GDC. And now what it wants me to do is press the tab button. That gives you an extra function. And it just wants us to type in what we just did. So 8.6. Remember, we can't write D. Make sure we write it in the right place. That always helps. 8.6. And we can't write D. We write X instead. And notice this gives us a similar looking graph here. I'm going to take a quick screenshot. So instead of actually drawing the sketch again, just so you've got that for your own reference as well. And let's make that a little bit smaller so it fits in nicely. So there we are, we've got our two graphs. So I've done that part there. What you would do in the exam is actually go back and then sketch it on here. So you do this in a different color. So it starts a little further across and then crosses the graph and then continues in this direction. Okay, and one of the reasons we've done this, so we've done this part here, is find the height of the half cylinder. Now looking for the height here, this is important, that fits both models. So first of all, we want to work out this intersection point here. So that will work out our D. So by working out this intersection point, we're going to work out the diameter. Let's go and do this now. So we go to Menu, Analyze Graph Intersection, click before, click after, and then we read off the X value here, which is equal to 2.96. It's not going to be our final answer, so this is going to be 2.96, because remember we're looking for the height of the enclosure, and if we go back, you'll see the height here is not actually the diameter, it's the radius. So the way we work out then the actual height is we just take that answer 2.96 ... and divide by 2. You can obviously do this on the calculator and you'll get 1.48 ... So I'm going to pop that across, so 1.48 meters. Not as hard a question as it looks. Remember, use your graphical calculator. You do not need to solve this algebraically. And then our last question here is write down which enclosure of volume 10 cubic meters, cone or half cylinder, is most appropriate. Well, I'm going to use the answer we literally just got here. So notice we have a height of 1.48 meters. So we worked this out using the information given as 1.48 meters. But remember that in question A here, the smallest value of this is 2. So I'm going to say the cone is better, or should be chosen. And the reason for this is the half cylinder has height, so I'm just using what we've literally just worked out, has height 1.48 meters, and this is less than 2 meters. So I've given my justification to get that mark there. Okay, check the solutions that I've just gone through so you can see everything there in front of you in case you're unsure about anything, and there's the very last part there as well. Thank you for watching. If you need any more practice with paper 6, then check out the playlist right in front of you, because I've gone through a ton of iGCSE paper 6 videos, and if you like the content, then please do press like. It would be really, really helpful for the channel. Right, bye bye.